Welcome chemists, Mr. Gopal here, and today we're going to continue our exploration of chemical bonding by looking in detail at covalent bonds. And so specifically, when we look at covalent bonds, we want to think about them in comparison to ionic bonds. And so what I'm going to do in this video is I hope to just review the basics of ionic bonds, then talk a little bit about how covalent bonds are markedly different, both in makeup and behavior, and then take a look at a few Regents questions and see how these concepts are manifest on the exam. And so our quick journey back into ionic bonds, I'm going to write some things as I talk, just so you got something to see on the screen. Ionic bonds, if you recall, are between a metal and a nonmetal. And they involve the transfer of electrons. And so last time, taking a look at the periodic table on the reference table. And when we looked at that, we realized, there we go. Sorry about that text there. We realized if we're thinking about bonds between metals and nonmetals, our metals are everything to the right of this little staircase that you see blackened in a little bit thicker there. Our nonmetals, the small group of elements to the right of that staircase. Okay, metalloids exist on the staircase. But if we're bonding metals and nonmetals, then we're bonding these elements over here that have very low electronegativity, means they're not very attracted to more electrons, with these elements over here that are, because they're just, especially in like group 17, the halogens, they are just one electron short of a full outer shell. These ones have one or two too many. In group 1, they have one too many. In group 2, the alkali earth metals, they have two too many. So these elements over here really want to give up electrons. These elements over here really want to take them, because that great disparity in electronegativity, which means the attraction to more electrons, there's going to be a full-on transfer of electrons. And that's why when we're making, when we're drawing Lewis dot structures, we'll have brackets, we'll have a charge on each of these elements. We'll have a positive charge on the ones that give up electrons and a negative charge on the ones that take them, because there will be an imbalance between the numbers of protons and electrons in the elements involved in an ionic bond. On the other hand, when we think about covalent bonds, we're talking about two nonmetals over here that are bonding. And because they're more similar in electronegativity, they're going to be sharing these electrons. Both of these elements will need the electrons to fill their outer shells, but they are not transferring them. As a result, they are setting up a molecular structure that allows them to share. And so there's an example of that on the slides. Let me clear the text here. Let me see, yes. And so we can see this example of a classic covalent bond, CH4. We can see the green valence electrons in carbon, the blue valence electrons in carbon, the red valence electrons of hydrogen. And we see that we're able to pair each of the lone outer valence electrons for hydrogen with one from carbon, so they can fill their outer shells, which have two, because they only have one electron shell. And we can see carbon will take in the 4 electrons that are shared from hydrogen, and will be able to complete their outer shell of 8. Now, along with these bonding differences, there are other things to consider that we're going to go over in the future, like polarity of these bonds. What I mean when I say polarity is that one of the elements is always going to be more electronegative than the other, unless we're bonding the same element with itself. Okay, so in those cases, the more electronegative will have a stronger pull for the electrons. So there will be an imbalance, and there will be sides to the bond that have a more negative charge and a more positive charge. For now, though, we also just want to take a quick look at some of the characteristics of these bonds. So Covalent compounds, they do burn easily. On the other hand, ionic compounds do not. They don't have freely moving electrons. This goes along with when we were studying the elements in some of the initial units, the idea that nonmetals are poor conductors of electricity, while metals are great conductors of electricity, because metals have more free floating, especially the transition metals, have more free floating electrons. They conduct electricity very well. Covalent compounds do not. Covalent compounds generally don't dissolve in water. Ionic compounds will dissolve very well in water. And then the individual molecules of covalent compounds are more easily separated than the ions in a crystal. That has to do with the strength of certain bonds. So because of the relative weakness of certain bonds, covalent compounds will have lower boiling points than ionic bonds. And so hopefully you're starting to see in a lot of cases that bonding characteristics can allow us to be predictive about the behavior when certain elements bond with each other. And we can find patterns in that. And so actually, I'm going to skip ahead past that. And let's take a look at a few Regents questions. All right. So it says, which terms identify two different categories of compounds? And so this is a little bit tricky, and I want to go through the terminology here. So we have 4 answers, and those answers involve 4 different vocabulary words. We have the words covalent, molecular, empirical, and ionic. All right. And so the tricky thing here is that covalent bonds are sometimes referred to as molecular bonds as well. All right. And so the correct answer here would have to be 3. All right. Let me break it down. Since number 1 is saying the same thing in 2 different ways, those could obviously not be 2 different categories of compounds. Covalent compounds and molecular compounds are the same category of compound. Empirical is a term that we'll use when we talk about writing out a chemical formula within the lowest possible terms. Okay, so if, for example, I had, let's say I had C4H8. All right, I could, just like I would if I had the fraction 4/8, and I could say, oh, 4/8, I could reduce that to 1/2. I know that these are in a 4-to-8 ratio, 4 carbon atoms, 8 hydrogen atoms. So I can reduce both, and I can say this is the same as CH2. And that would be the empirical formula, whereas the molecular formula would be the original one, which takes into account the exact amount of atoms in that particular one. The empirical formula is chemically equivalent, but we don't actually know the exact amount of atoms. So we get more precise information from that molecular formula. And so that's how you do that first question. Now, I'm not going to talk about the answer to the next one, but I do just want to talk about a few characteristics of a typical Regents chemistry question. So very often I tell my students to jump ahead to the question. And that's because on short answer questions and even some multiple choice questions, they will often have long descriptions of something that's interesting, but it's not necessarily related to what you're being asked about. So we've got this long thing about a thiol and the similarities and differences between a thiol and alcohol. If we skip over that, we see that the question is asking us to explain in terms of electron configuration why sulfur atoms and oxygen atoms form compounds with similar molecular structures. And so we can see an example there that shows sulfur atoms, all right? But we could also picture, particularly with water, we could picture how there are chains of bonds that have a similar structure to the way that we see dimethyl disulfide and methane diol in the molecular structure in the diagram. And so part of the answer lies in the periodic table of elements. It was such an important unit. We studied trends in the periodic table. And all we need to do is go over here and take a look at this. So I could have circled this entire group or family, group 16. And the reason I could have circled the entire thing is if we go through, I'm going to zoom in a little so it's easier to see. If we go through, clear that, and we take a look at all of the electron configurations for elements in group 16, we'll see that they all end with 6 valence electrons. This 6 valence electron in the outer shell structure will make all of these elements in this group bond in similar ways because they have 6 electrons to either share or add to in, say, an ionic bond transfer. And so if we look here, it's obvious that oxygen and sulfur would bond in similar ways because of their valence electrons. They have the same amount. Therefore, if they were combined with some other element, either one would probably combine in a similar molecular structure. So in conclusion, covalent bonds between 2 nonmetals, because nonmetals are high in the amount of electrons in the valence shell or the outer shell, there's going to be often a sharing of electrons between 2 different nonmetals because they both want to fill their shells. And this sharing is going to lead to interesting structural patterns when we create a molecular structure for these bonds. And there's no transfer of electrons, unlike with ionic compounds. I hope this has been helpful, and I will see you soon.